The length of a moving object is measured to be shorter than its rest length. Known as length contraction, this complex idea from the theory of special relativity reveals itself in this seemingly simple and easy to carry out experiment. In 1905, Albert Einstein, while still working as a patent clerk, discovered the special theory of relativity, which challenged the conventional belief that time and space could be defined separately from each other. Rather, space and time in special relativity are interwoven into a single continuum known as space-time. The space-time coordinates of two frames in relative motion with constant velocity are linked by the Lorentz transformations, application of which leads to a number of bizarre outcomes, one of which is the length contraction of moving objects. To elaborate, let us take an example. Imagine two observers, Alice and Bob, both trying to measure the length of a rod that is lying parallel to the x-axis and moving with constant velocity v along the x direction. Alice is at rest in xy frame while Bob is moving with the rod. If Bob measures the length of the rod to be L prime, then what would be its length measured by Alice? Well, contrary to our intuition, it will be L prime multiplied by square root of 1 minus v over c squared, where c is the speed of light. Since relativity also mandates that v can never be greater than c, the length measured by Alice will always be shorter than that measured by Bob. This shortening of the measured length of a moving object along the direction of motion is known as relativistic length contraction. So far, it has not been possible to test relativistic length contraction by direct experiment, but that doesn't mean that there is no evidence at all. After all, Einstein's paper on relativity was titled "On the Electrodynamics of Moving Bodies" for a reason. So, let's do an experiment and see relativity in action. Here we have, mounted on a piece of cardboard, two parallel segments of a wire, the ends of which are connected to a 5-volt power supply. If the wire is configured like the schematic shown, the current flowing through the two parallel segments will be in opposite directions. Now, as the current is turned on, you can see that the wire segments are repelled from each other. Let's zoom in for a clearer view. The glowing blue LED indicates that current is on. On the other hand, if the directions of current in the two segments are made same by changing the wire configuration, as shown in the schematic, the segments come towards each other. It means they feel an attractive force when the current is on. As we may already know, these experiments are demonstration of Lorentz force that the moving electrons in one wire experience due to the magnetic field created by current in the other wire. So where is relativity in these? Well, to see special theory of relativity in action here, we have to put ourselves in the shoes of the electrons, literally. We consider a model up to infinitely long, thin parallel wires carrying currents I1 and I2 in opposite directions. The x and y axes shown here belong to a frame of reference in which the wires are at rest. The idealized wires have linearly distributed equidistant positive ions at rest, shown by the plus circles, and negatively charged equidistant mobile electrons, shown by the minus circles. The electrons are moving with constant velocity v1 along the positive x direction in wire 1 and with velocity v2 along the negative x direction in wire 2. As is well known from experiments, current-carrying conductors are electrically neutral in their rest frame. It means that in xy frame in which the wires are at rest, the line charge density of the fixed positive ions and that of the mobile electrons are the same in each wire, so that there is no electric field outside the wires. However, let's see what happens if we move to the frame of reference of the moving electrons in one of the wires, say wire 2. In the frame of the moving electrons in wire 2, let's call it the x' y' frame or simply the prime frame. Everything except the electrons in wire 2 are in motion. These include the ions in wire 2 and both the electrons and ions in wire 1. It is trivial to see that the velocity of the ions in wire 1 in this frame represented by v' plus is v2. However, to calculate the velocity of the electrons in wire 1, that is V prime minus, we have to resort to Einstein's velocity addition rule, according to which the velocity of the electrons in wire 1 is equal to the sum of V1 and V2 divided by 1 plus V1 dot V2 over c squared. Now that we know the velocities of the ions and the electrons in wire 1 in the x prime y prime frame, we can calculate their charge densities. We have seen that in the laboratory frame, which is the rest frame of the wires and also of the ions, the spacing between two neighboring ions is L. Therefore, from the ideas of relativistic length contraction, the spacing between the positive ions in the prime frame L prime plus is L multiplied by square root of 1 minus V2 over c squared, which is represented in the terminology of relativity as L over gamma 2. Now let us turn our attention to the electrons in wire 1, calculating the spacing of which is not straightforward like the case of ions. We have to first calculate the separation of the electrons in their rest frame. Remember that in the laboratory frame, the electrons in wire 1 are moving with velocity v1 and their separation is L. Therefore, if the separation of the electrons in their rest frame is L0, then as per relativistic length contraction, L equals L0 multiplied by square root of 1 minus v1 over c squared, which can be rearranged as L0 equals L multiplied by gamma 1. Once L0, that is the separation of the electrons in their rest frame, is known, it is easy to calculate their separation L prime minus in the prime frame by applying again the expression for length contraction. As shown in the screen, after some algebraic simplification, L prime minus becomes L over gamma 2 multiplied by 1 plus v1 dot v2 over c squared. Therefore, from the expressions for L prime plus and L prime minus, we see that in the frame of the moving electrons in wire 2, the separation of the positive ions in wire 1 is more than that between the electrons. As the charge density is inversely proportional to the spacing of the charges and charge is invariant, the charge density of the positive ions in wire 1 in the prime frame will be lambda multiplied by gamma 2. Whereas that of the electrons will be minus of lambda multiplied by the product of gamma 2 and 1 plus v1 dot v2 over c squared. So, there will be a net negative line charge density of magnitude lambda multiplied by gamma 2 v1 dot v2 over c squared in wire 1 in the prime frame. It is an interesting result. Whereas wire 1 is electrically neutral in the laboratory frame, it is negatively charged in the frame of the moving electrons in wire 2. The negative line charge density in wire 1 will create an electrostatic field surrounding the wire, the magnitude of which can be calculated at the position of the wire 2 by simply applying Gauss's law. Each electron in wire 2 as a result feels a repulsive force F21 prime along the negative y direction. In the same way, from the perspective of the electrons in wire 1, wire 2 is negatively charged and the electrons in wire 1 as a consequence feels a repulsive force F12 prime. Since there is force on the electrons in both the wires in the x prime y prime frame, perpendicular to the direction of motion of the frame, there will be force on the electrons in the laboratory frame as well in the same direction. The magnitude of this force in the laboratory frame can be calculated using the relativistic transformation rule for force, which for the electrons in wire 2 gives the magnitude as F21 prime divided by gamma 2. Since the electrons in each wire are bound within the respective wires, the wires will also feel the repulsive force. If the number of electrons per unit length in wire 2 is N2, then force per unit length in wire 2 is simply N2 multiplied by the force experienced by each electron. Using the expression for C in terms of permittivity and permeability of free space and considering the relation between charge density and current, the magnitude of the force per unit length in wire 2 in the laboratory frame is μ0 I1 I2 divided by twice pi d. The symmetry of the expression with respect to I1 and I2 implied that the force per unit length in wire 1 is also the same. The force experienced by the wires in the laboratory frame is not electrostatic in nature, as there are no charges on the wires in that frame. This force depends on the magnitude of the currents in the wires instead of charges and is known as the magnetic force. The relation for the force that we arrived at using the concepts of relativistic length contraction is nothing but the well-known expression for the magnetic force acting between two current-carrying conductors that we previously demonstrated experimentally. Therefore, the very existence of the magnetic force between current-carrying conductors is a consequence of relativistic length contraction. We should, however, remember here that the drift velocity of the electrons in metals is really small, to the tune of few millimeter per second, for which the length contraction should be negligibly small. But the fact that we still see the manifestation of relativistic length contraction is due to the huge number density of electrons in metals, about 10 to the power 23 per centimeter cube, so that the small effect per electron is magnified many times to produce the macroscopic effect.